Okay, hello everyone, and welcome to our next lecture in Intro to Analysis. So, in the last lecture, we left off on fields. We're going to pick back up there. We're going to talk about upper and lower bounds and supremums and infimums. And depending on where we are time-wise, I might add some things at the end of this video. Okay, so back to fields. So in the last video, we talked about Q, rational numbers, and the real numbers R being fields. Why can't we do analysis with Q? Well, we don't have a notion of continuity with Q, right? If I were to draw a line segment from 0 to 1, yes, I have infinitely many rational numbers between 0 and 1, but I also have infinitely many irrational numbers between 0 and 1. Right, so for the rationals, I have a half, I have a fourth, I have an eighth, and so forth, right? I can just keep having again and again and again, and I get an infinite sequence of shrinking rational numbers. But I also have things from 0 to 1 that are irrational, such as square root of 2 over 2. That lives in 0 to 1, and there are infinitely many other real numbers that are not rational that live in this interval. Okay, so there's not a notion of continuity if we just use the rational because of these gaps. The rationals because of these gaps. We also want our number system to be closed under things. So in the last video, I talked about rationals and reals being closed under addition and closed under multiplication, right? We want to extend this notion to analysis concepts. We want sequences of numbers to converge to a number in that set. And the problem here with the rationals is that we can construct a rational sequence where all of the elements in the sequence are rational, but it converges to an irrational square root of 2. And I'm not going to prove that here. We'll take that for granted. We'll show that a little bit later. But the idea here is that the sequence, we have the first term in the sequence is 2, and then we follow this rule for the rest of them. So the next one, a sub 2, is going to be a half times a sub 1, which was 2, plus 2 over a sub 1, which was 2. And so this is going to be 3 halves. And the next one is going to be approximately 1.4167, well, equal to 1.4167, and so forth. And this is eventually going to converge to the square root of 2. So everything in our sequence is rational, but we're converging to an irrational. That's an issue. So the idea is we want our number system closed under limits when we are looking for when we're looking for limits of sequences. Another issue here with Q is that it's not algebraically closed. And what that means is that you can have a polynomial with coefficients in Q. So here the coefficients are 1 and negative 3, but the roots are not in Q. So that means it's not algebraically closed. So x squared minus 3 equals 0. We get x is equal to plus or minus root 3. These guys are irrational, so we want our number system to be algebraically closed as well. If we take the roots of a polynomial and real coefficients, we want those roots to be real. So how do we fix the issues with Q? Well, the idea, and this is very imprecise, is to throw in numbers to complete Q. And we'll talk about what it means rigorously to complete Q later. But intuitively, you can think of just taking, like, for instance, if you're looking at all of the rationals between 0 and 1, just completing it, meaning throwing in every real number so that the line segment from 0, 1 is completely continuous. There's no gaps anywhere. Okay, so what we need to complete Q, to make it R, is we need the axiom of completeness. And I'm just going to state it for now. And then we'll come back at the end of the lecture once we get all of the tools that we need to talk about this, and explain it a little bit more at the end of the lecture. So I'm just going to state it for now. Every non-empty set that's bounded above has a least upper bound, and the goal of this lecture is to decipher what that means. So first thing we're going to talk about is what does it mean for a field to be ordered, because it turns out the real numbers is an ordered field, right? We have the field axioms like closure, inverses, etc., but we need some other axioms in order to make distance precise. So an ordered field is just a field F with the following axioms, and so here's the order axiom. There is a non-empty subset P contained in the field of non-zero elements called positive elements, and they have the following properties. If you have two numbers in that positive set, then it's closed under addition. So if A and B are in the positive set, A plus B are positive. And also A times B is positive. So you can just think of real numbers, why this makes sense. If A is in your field and A is non-zero, then either A is positive or negative A is positive, but not both, right? You can't have two numbers being positive and negative at the same time. Okay? And so from these axioms, we get some really nice properties of the reals, because as I mentioned, the reals are ordered. And so here they are, and it's not too difficult to verify these. I'm not going to, but if you don't believe any of them, you should try and check yourself. But these are all things that you know intuitively from just working with numbers your whole life. So the first one is if a number A is less than B, then A plus C is less than B plus C. It's pretty straightforward to see. Just add C to both sides. Let's see. The next one is if A is less than B and B is less than C, then A is less than C. Sometimes this is called transitivity. Then you have this inequality reversing notion that you've done in Algebra 1 to Calculus, all of these things. So the idea is if you have A is less than B, then AC is less than BC if C is positive. Okay, so when you multiply both sides by C, you don't flip the sign if that C is positive. And then you do flip it if the C is negative. So for instance, if you have this and you multiply both sides by -2, you end up getting this. You flip the inequality sign. Okay? If A is non-zero, then A squared is positive. That's pretty intuitive, I think. Also, I just want to make a side note. I write these little gold stars to indicate that this is important and you're probably going to use it in many of your proofs down the road. So just keep that in mind. Those 3 gold stars, it means, hey, it's important. Okay, the next one is if you have 2 positive real numbers, one's bigger than the other, then it's order reversing when you take the reciprocal. So for instance, if you have the number 3 is greater than 2, well, that means that a third is less than a half. So the order reverses when you take the reciprocal. Well, yeah. Okay. The last one, if you have A is less than or equal to B and B is less than or equal to A, then A and B have to be equal to each other. This falls right out of order axiom B. Okay, so you can't have A is less than B and B is less than A at the same time, right? Okay, so that's also an important little property that you'll come back to again and again. Okay. So now that we have an ordered field, i.e. the real numbers, we're building ourselves up to study convergence, limits, notions of distance. And so we need a distance function, and that's going to be our absolute value function. So by definition, the absolute value function is a function from the reals to the reals. So we're inputting a real number into the function. We're getting out a real number as well. And this is the definition of it. So the absolute value of x is just x if your number is bigger than or equal to 0, and it's negative x if your number is strictly less than 0. So for example, if you're trying to take the absolute value of 8, since 8 is bigger than or equal to 0, it's just equal to 8. Okay, negative 8, if you're taking the absolute value of that, well, since negative 8 is less than 0, it's going to be negative 8, which is just positive 8. Okay, so one way to think about absolute value of x that I find helpful is to just think about the distance between x and 0 as the absolute value of x. So for 8, the distance between 8 and 0 is 8, but also the distance between negative 8 and 0 is also 8. So we can't, because this is a distance function, we never define distance as being negative, so it's always going to be positive. This absolute value function is always going to have a positive output. Now, these are other properties that you'll use in your proofs at some point, and I think all of these are easily verified, so I'm not going to spend the time doing that here, but if you want some more details about this, you should maybe talk to me in office hours, but it's a good exercise to prove these little properties by yourself. So the first one is what I just mentioned. The distance is always going to be 0, bigger or than or equal to 0, and equality only if a is 0. Okay, so distance function has to be positive or 0. The distance from a number to 0 is the same thing as the distance of negative that number to 0. We saw that in the previous example here. This is easily verified as well. A is greater than or equal to negative apps A, less than or equal to apps A. The absolute value function is multiplicative, meaning that if you take the absolute value of A times B, you can break it up as apps A times apps B. So for instance, if you have like x plus 3 times x plus 2, you can break it up as apps x plus 3 times apps x plus 2. Okay, that's all it's saying. And then this last one, G. So the quotient ones are similar to the multiplicative case. And of course, you can't have a denominator being 0. That's that little statement there. The last one is important in proving things too. So it's just saying if the distance from 0 to A is less than or equal to B, then A has to live between negative B and B. And I think that's pretty clear if you draw a picture and think about it for a moment. So here's 0. Now A could be, so here's negative B and here's B. So if the distance between, and maybe I didn't draw it exactly equidistant, but forgive me. Here's 0. So if the distance from 0 to A is less than or equal to B, then it's either going to live, A is going to live in this region, or A is going to live in this region. And that's all this is saying. A is between negative B and B. Okay, so this is a pretty useful one. Okay, so this is a super important theorem that you're going to see over and over again. It's called the triangle inequality. You may have seen it in a previous class, I'm not sure. But the reason they call it the triangle inequality, and I think your book goes into this, but so here we have, let's say this is from A to C, let's say this is a B to C, this is apps Y, this is apps X, and this is apps X plus Y. And so all this is saying is that the shortest distance from A to C is always going to be this straight line, right? So this is going to be shorter than going this way and then this way. Or it could be equal if this guy is a right triangle. Okay, so that's kind of the intuition behind why this is called the triangle inequality. Now let's go ahead and prove it. So I'm going to show this. I guess I'm just going to write it out. So to show, I want to show this guy. But instead, what I'm going to do is I'm going to work with the squares because we're dealing with all positive values, and so squaring shouldn't cause any kind of problems with the absolute value signs. So I want to show this. We will show that x plus y squared is less than or equal to apps x plus apps y squared, right? So again, this is if and only if this is true, right? The squares really have no bearing on the inequality we're trying to show because we're in absolute values, we're adding everything as positive. So I'm going to show this instead. Okay, and so to do that, I'm going to first start with this guy right here, and I'm going to expand it and play around with some things. So I'm going to start with this, apps x plus apps y squared, and that's going to just be equal to the expanded version here. Okay, and so I can just distribute. And so what do I get? Well, I get this squared plus 2 apps x, xy plus y squared. So because squaring is always going to produce something positive, I can just say that apps x squared is the same thing as x squared, and likewise with apps y. So this is the same thing as x squared plus 2 x apps x apps y plus y squared. And then I'm going to write a little side note over here. So notice that the absolute value of x times the absolute value of y is always going to be greater than or equal to xy, right? Depending on what the signs of x and y are going to be. So you should convince yourself of this if you don't believe it, but hopefully you do. So this is going to be greater than or equal to x squared plus 2xy plus y squared. And then we can just condense this into x plus y squared, which because of the square, it's the same thing as apps x plus y squared. Okay? So we're done because we've shown that this guy is greater than or equal to this guy. Thus, and I'm just writing it backwards to how it was stated, but x plus y squared is less than or equal to this guy right here. And this implies that apps x plus y is less than or equal to apps x plus apps y. And we are done with our proof here. So that's the proof of the triangle inequality. And I think your book, let me see. I don't know if your book does the proof like this, but if it, let's see. Well, I think they do it slightly different. Yeah. But anyway, it's good to see different routes to doing things, I think. So anyway, well, it's not my proof of the triangle inequality, but it's a proof. And so let's go ahead and use this thing. Now, what do we have here? We're told that x is between -2 and 1, strictly. And we want to show that this implies that the absolute value of x squared minus x is less than 6. We're going to make use of the triangle inequality here. So the key observation here is we want to eventually, just looking ahead, if we're using the triangle inequality, I'm going to end up seeing an abs x coming up in some form or another. So I want to say something about the absolute value of x, right? Based on the fact that x lives between -2 and 1. So drawing our little picture here, here's -2 and here's 1. I know, what a great picture. Don't all applaud at once. But yeah, anyway, so here's 0. Let's just say 0 is right here. So if x is living in this interval from -2 to 1, what could the max value of abs x be? And I'm just being lazy. I don't feel like saying absolute value, so I'm saying abs x. Well, we can see here that the distance between x and 0 at the very maximum is going to be 2, but not equal to 2, right? Because of this open parenthesis here. So we know that the distance between x and 0 better be less than 2. Okay, so, right, because x could be here, it could be here, it could be really close to here, or it could be over here somewhere, but anywhere you put it, that distance between x and 0 is smaller than 2. Okay? All right, so we know this. So now let's use the triangle inequality. By the triangle inequality, we have, well, x squared minus x. This is equal to, I'm just writing all the steps out just so you see it. Okay. Now, triangle inequality says abs a plus b is less than or equal to, I'll write it up here actually. Abs a plus b is less than or equal to abs a plus abs b. So choosing this as a and this is b, quote unquote, this is going to be less than or equal to abs x squared plus abs negative x. And I can bring that square out to the front, right? Because abs x squared is the same thing as abs x squared. Because, you know, we're just dealing with positive numbers here. So that's the same thing here. And then this guy, distance between negative x and 0 is the same as distance between x and 0. So this is just plus x. Okay, and by this up here, since this guy is less than 2, we have that this whole thing is going to be less than 2 squared plus 2, right? Because abs x is less than 2, therefore this is going to be less than 4, therefore be less than 2. Oh, I hope that didn't mess up anything. I guess I have to charge my pencil and come back. Yeah, okay, cool. So that's equal to 6. And thus, x squared minus x is going to be less than 6. And we're done. I'm going to charge my pencil and come back in a minute. Okay, so let's go ahead and prove this nice little corollary of the triangle inequality, which is called the reverse triangle inequality. And I'm going to show you a little trick that can be really, really useful. Okay, so here's the useful trick. The absolute value of y, we can write it in a sneaky way as the absolute value of y minus x plus x. Right? Negative x plus x is just 0, so this is the sneaky trick so that we can use the triangle inequality, right? Because now we have two things inside the absolute value bar. Okay, so by the triangle inequality, we have y is equal to, well, we just defined it as this. And this is going to be less than or equal to, well, you see I'm breaking it up as follows. Y minus x plus abs x. And this is equal to, well, if I just pull a negative out of here by our properties that I listed, oh, why can't I write today? I don't know. All right, these are the same thing. This is the same thing. So, and this simplifies to x minus y plus x. And so if you rearrange this, well, you get absolute value of y is less than or equal to abs x minus y plus abs x. And so we have, if we just do the subtraction, we have the absolute value of x minus y is greater than or equal to abs y minus abs x. Okay, so we'll keep this in mind. Okay, similarly, we can do the same trick with the absolute value of x. So we have same trick. We have that the absolute value of x, because we're trying to like split it off into two terms so that we can use the triangle inequality. So this is the same thing as abs x minus y plus y. And by the triangle inequality, and actually I should have put this up here. I'm just gonna add it there. Triangle inequality, that's true. So this is less than or equal to abs x minus y plus y. And again, this is because of the triangle inequality. And therefore, the absolute value of x is less than or equal to abs x minus y plus abs y. And rearranging, we get abs x minus y is greater than or equal to abs x minus abs y. Okay, so we have these two things here, and so notice that abs y minus x is just equal to negative abs x minus abs y. So we have okay, so since we know this, it follows, and you should check this if you're not sure immediately, from proposition 1.2g, that this means that the absolute value of x minus y is going to be greater than or equal to abs x minus abs y. And we're done. Okay, so these two statements right here by proposition 1.2g imply what we wanted, our reverse triangle inequality. Okay, so I've been kind of implicitly mentioning this throughout the lecture, but this is where the definition comes up in the book, so I thought I'd stick it here. Suppose you have two real numbers, x and y. We want to define the distance function with the absolute value. So R cross R into R. So you start in R cross R. That means you take something from R and you take something else from R. And that distance function is going to result in something in R. So like, you know, here it is. So the distance between 5 and 1, for example, is just going to be the absolute value of 5 minus 1, which we know is 4. So we took something in R cross R, something from R, and we end up in R. Okay, that's the output of our function. Okay, and so like, you know, same idea here. We have abs negative 3 minus 2 is equal to 5. Okay, so the distance between negative 3 and 2 on the number line is 5. Okay, so now we're going to talk about a bunch of definitions that you should probably get tattooed on you at some point. No, I'm just kidding, but remember them. Okay, so the first definition is bounded above. All right, so A is contained in R as a subset of R, non-empty, and it's bounded above if there's some B in the reals so that X is less than or equal to B for all X in our set A. We call B an upper bound of A. Okay, so I'm just going to illustrate this with a little picture. I'm going to say our set is from 0 to 1, the open interval from 0 to 1. And let's think about some upper bounds for this. Okay, well, there are a lot of numbers that exceed every number in this set, right? So how about 2? And maybe I'll just put B equals 2. B equals pi. You know, B equals a trillion. I don't care, okay? There's infinitely many upper bounds for this set, right? Because anything in the set X is going to be smaller than or equal to these upper bounds. Now, what about 1? Is 1 an upper bound of the set? Is everything in the set smaller than or equal to 1? Well, yeah. I mean, no matter how close you get to 1, you're always going to be smaller than 1, right? So it's strictly smaller in this case. And that brings me to the next definition. The least upper bound of A is some B naught in the real such that B naught is an upper bound of A, and if B is any other upper bound of A, then B naught is less than or equal to B. Okay? So 1 in our case, let me write it here. So 1 is the least upper bound of our set A. Okay, why is this? Well, 1 is certainly an upper bound. We argued that in part 1, right? Everything in the set is smaller than or equal to 1, specifically smaller than 1. And if you have any other upper bound of A, then 1 is going to be less than or equal to it. So if we look at our picture here, 2 is an upper bound, pi is an upper bound, 1 trillion is an upper bound. 1 is always going to be less than or equal to all of those upper bounds. Okay, so that's the idea here. We give the least upper bound of a set A a special name, and we call it the supremum of A. So we would say here that, or soup, if you like soup. I think the author in this book makes a joke, soup Nazi, referring to that episode of Seinfeld, if you guys have seen it. But I don't know, I thought that was pretty funny, and honestly, it really pulled me into this book, that soup Nazi joke. So in our case here, the soup of the open interval from 0 to 1 is 1. Okay, it's the least upper bound. All right. All upper bounds are larger than 1. So 2, pi, a trillion, yada yada. Okay. And so we have an analogous definition for the lower bound, bounded below, etc. The set A is bounded below if there's some b in the real numbers such that x is bigger than or equal to b for all x in my set A. Okay, so I'm going to just do the example from 0 to 1. We're going to do more examples in the coming slides, but I don't know, I like this one. So, you know, I'm just going to do it. So here is our real line in all of its glory. And here's everything in our set A from 0 to 1, but not including our endpoints. So bounded below. So let's find some lower bounds. Well, -1 is a lower bound, right? Because everything in the set is bigger than or equal to -1. That's true, isn't it? So -1 is a lower bound. I don't know. Negative 8 is a lower bound. You know, -0.5 is a lower bound. -1 billion is a lower bound. All of these things are lower bounds. There's uncountably infinite many lower bounds for this set. And what do you think a greatest lower bound is? Excuse me. A greatest lower bound. What do you think it is for this set? Pause the video and ponder a little bit. What do you think the greatest lower bound is? Well, it's some real number so that it's a lower bound of A, first of all. And if there's any other lower bound of A, then that bigger bound has to be bigger than or equal to the lower bound. Okay? So what does this say in plain English? Well, think about all of these purple numbers. How close can we get to bounding this set? How about -1 over a trillion? That's a lower bound, right? It's getting really close to 0, right? In fact, 0 is a lower bound because everything in the set does not include 0, everything in the set is greater than or equal to 0. In fact, greater than, okay? So in 0, 1, maybe I'll write this in red. In 0, 1, 0 is a lower bound. And in fact, it's the greatest lower bound. Right? You cannot pick something larger than 0 so that everything else in the set is bigger than or equal to it, right? Think about that. Really think about that. You know, if I said, oh, well, how about 1 over a trillion? Well, 1 over a trillion and 1 is smaller than that. So 1 over a trillion is not a greatest lower bound. You see? You see where this is going? Okay, so it's kind of an interesting thing to think about, right? Okay. So 0 is the greatest lower bound. There is nothing bigger than 0 that is a lower bound for the set, right? Think about that. Okay, so we also call the greatest lower bound the infimum of A, and that's how I'm going to refer to it from here on out, I think. If a set is bounded above and below, well, guess what? It's bounded. Now here is the kicker, okay? In calculus, you talk about maxes and mins of sets. Now, maxes and mins actually have to be contained in the set. If I asked you, what is the max of the set 0, 1, you couldn't tell me 1 because 1 has to be in the set and it's not. It's not included by that parentheses. However, sups and infs do not have to be in the set. So we know that the sup of 0, 1, the least upper bound is 1, is not in 0, 1. And also, the infimum, the greatest lower bound of 0, 1, which we said was 0, is also not in 0, 1. And that we have no problem with that, okay? So that's the difference between sups and infs versus maxes and mins. Maxes and mins actually have to be in your set. Now, if I change this just a little bit to have these little brackets, well, then my sup and my inf would actually be contained in the set because the brackets say, hey, this number is actually in here. But yeah. Okay, so let's do an example where we actually prove the supremum of the set is some number. So, for example, we have the closed interval from 0 to 1. We want to claim that the supremum is 1. So we want to show two things. We want to show first that 1 is an upper bound of 0, 1. And 2, 1 is the least upper bound of 0, 1. Okay? So for the first step, this is pretty easy. So what does it mean to be an upper bound of a set? It means that everything in the set is less than or equal to that thing. So since 1 is greater than or equal to x for all, this means this, I don't know if I did this little symbol in the last lecture, but this is for all, this upside down A. So 1 is greater than or equal to x for all x in 0, 1. Therefore, 1 is an upper bound of 0, 1. Okay, so for the second step, we want to show that it's actually the least upper bound. And remember what we have to show for that. We have to show if there's another upper bound for the set, then 1 is going to be less than or equal to that upper bound. Okay, so suppose that M is an upper bound for 0, 1. Then what does that mean to be an upper bound? That means that M is greater than or equal to x for all x in 0, 1. Well, 1 is in 0, 1. Right? Because of the brackets, it says that 1 is actually included in that set. And therefore, M is greater than or equal to 1, i.e. 1 is less than or equal to M. So 1 is the least upper bound of 0, 1. Right? We said, okay, let there be an upper bound of it, of 0, 1, and we showed that that upper bound is bigger than or equal to 1, i.e. 1 is less than or equal to the upper bound. Okay, so 1 is the least upper bound. And so we conclude that 1 is the supremum of 0, 1. Okay. So let's do some examples that aren't going to require proof. Let's just find the supremum and infimums and the bounds and things to get a feel for them. Wow, it looks like this N was written by an insane person. Let's do it a little bit better. Okay, so there's the natural numbers. So our first set is the natural numbers. Are the natural numbers bounded above or below? I'll recall that the natural numbers include 1, 2, 3, and so forth, just your counting numbers. So yes, they are bounded. They are bounded below, but they're not bounded above, right? Because this goes on forever and ever. You can never find a number bigger than or equal to every single number in the set. So the answer here is not bounded above, but it is bounded below, right? So remember, bounded below means that there exists a number such that all numbers in the set are bigger than or equal to that number. So bounded below by, for example, 1, 0, negative, 1,000, blah, blah, blah. Okay, so 1 is always going to be smaller than or equal to 1, 2, 3, 4, blah, 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 everything in the set. So is 0, so is negative 1,000, etc. Okay, so not bounded below, above, but bounded below. So the upper bounds, we just said there are none. You can always find a bigger natural number than the upper bound you choose. So there's no upper bounds. Lower bounds, we just mentioned all of these. 1, 0, negative 1,000, negative pi, I don't know. Anything that is going to be smaller than or equal to every element in the natural numbers will work. So what's the supremum of A? Well, there is none, right? There's no upper bound, and hence there's no least upper bound. The infimum is going to be 1, right? Because clearly 1 is a lower bound for the natural numbers, and for any other lower bound, 1 is going to be bigger than it. So, as I mentioned here, 1 is bigger than 0, negative 1,000, etc. And we're not going to do this with proof. You could prove all of these, but I'm gonna prove some other ones, but for now, I just kind of want you guys to get the intuition for what I'm talking about here. So think about the next one. What about the integers? Is this set bounded above or below or both? Well, the integers consist of all whole numbers, positive and negative. Okay, so no, the set is neither bounded above or below. You can always find a number smaller, so if you're at negative 3, you can say negative 1,000,000. If you're at negative 1,000,000, you can say negative 1,000,001. There's no lower bound here. And similarly, there's no upper bound for this set. So the answer here is just no. No upper bounds or lower bounds. No supremum, no infimum. Kind of boring, but that's why we're not doing analysis with the integers. What about this set? Okay, so we have our set is 1 over n, where n is a natural number. So it might help to just kind of list out what this is. So if we let n run through the natural numbers, 1 over 1 is 1, 1 over 2 is a half, etc. Okay, so is this set bounded above or below? So, yeah, I mean, we can just look at what's happening here. We are decreasing, right? We're the biggest the set is going to be is 1, right? We can never have this set be larger than 1. And so it's bounded above, certainly. Bounded above. And it is also bounded below because no matter how large we make n, we're never going to get to 0. We're going to get really, really close to 0. We can make little n as large as we want to, but we're never actually going to get to 0. So this is also bounded below. Okay, so the upper bounds. So anything that is bigger than or equal to everything in the set. I can think of infinitely many things. I can say, well, 1,000 is always going to be bigger than or equal to anything in the set. I can say pi. I can say the number e. I can say all kinds of things. And actually, I can say 1 as well, right? Because 1 is going to be bigger than or equal to anything in the set, right? So those are the upper bounds. The lower bounds, well, we already mentioned it's never going to get to 0. So 0 is a lower bound. Also negative numbers. So negative 300, I don't know, negative 5, 0. These are lower bounds. And so what's the least upper bound? What's the smallest upper bound we can possibly have? Well, that's going to be 1. We can't have a smaller number than 1 that is bigger than or equal to everything in this set. So the supremum is going to be 1, and the infimum is the greatest lower bound. That's going to be 0. Okay? And we're going to prove this eventually, I think, in this slideshow. But yeah, that's the idea here. Now let's look at another one. So we have the set A is n over n plus 1, where n is a natural number. I like to just start by writing some terms in my set. So if I let n vary through the natural numbers, I have 1 over 1 plus 2. I have 2 over 2 plus 3, and so forth. 3/4, 4/5. And you can see where this is going. Okay, so bounded above and below. So yeah, this thing is bounded above and below. You can actually, I mean, if you want to look on Desmos, you can see it too, that this is bounded above and below. This thing is going to be, sorry. So yes, the answer is yes. Yes and yes, bounded above and below. We can always find things that are smaller than or equal to everything in the set, and we can always find things that are bigger than or equal to everything in the set. So this thing is bounded above and below. So what are some upper bounds? Well, the bottom of this fraction is always going to be larger than the top, and so we're never actually going to hit 1 is the point here, okay? So the upper bounds, we can say, are 1, 2, 3, 1,000,000. I don't know. Okay. So yes, we have lots of upper bounds. Lower bounds, what things are less than or equal to everything in the set? Well, how about 1/2? 0, -1, half, and so forth. Lots of lower bounds. Okay, so what's the least upper bound? Well, that's going to be 1. Okay. And what's the greatest lower bound? That's going to be 1/2. As you can't have anything smaller than, you can't have a lower bound greater than 1/2. Okay. Okay. Let's do this example. So this is kind of similar to the one we looked at with 0 to 1. So here's our set. X is a real number between 0 and 2. Is it bounded above and below? Well, yes. I mean, you can just see here that we're going to have a bunch of lower bounds to the left and a bunch of upper bounds to the right of 2. So what are some upper bounds? I can say 2 is an upper bound because 2 is bigger than or equal to everything in the set. I can say 2.0001. I can say 100. I can say anything bigger than 2. Lower bounds, I can say 0 is a lower bound because 0 is less than or equal to anything in the set. I can say -8. I can say -100, whatever. The supremum is the least upper bound. So that's going to be 2. And the infimum is going to be 0. Okay, just like that example with 0 and 1. And let's look at this set right here. So let's kind of list out what's happening here. All right, so the only thing that is going to change with respect to the numerator is whether it's going to be a positive or a -1, right? If m is even, it's going to be a +1. If m is odd, it's going to be a -1. So this is going to be equal to -1/n if m is even, or sorry, if m is odd, and it's going to be 1/n if m is even. Okay? So if we think about the things that are in this set, well, we could have something like, you know, I don't know, -1/100, -1/3. We could have 1 is in there. We could have 1/2, 1/8, things like that. I'm not writing these in order, but but anyway, what's the point? The point is we're trying to figure out what the, well, I haven't given myself enough room, so let's just look at what the supremum and the infimum are. So it's the supremum. What's the largest value that we are converging to here in our set? Well, it has to be 1, right? 1 is the largest possible thing that is going to be in this set, and it's the least upper bound of this set. Okay, so the supremum is going to be 1, and the infimum, if we think about it, is going to be -1, right? Because if m is 1, or really any odd power, and n is 1, then that's definitely an element in our set. So our infimum is going to be -1. And you should convince yourself of this just by listing out elements in the set to prove to yourself that there's no other, there's not going to be a smaller upper bound than 1, and there's not going to be a bigger lower bound than -1. Okay? Getting back to the axiom of completeness. Okay, so the idea here is that we're going to complete Q by taking every set of Q and throwing in its least upper bound. Okay, so to illustrate this with an example, let's consider the set of rational numbers S such that everything in the set is a rational number and this inequality holds. Okay, r squared is less than or equal to 2. And so the question is this set bounded above? And you could say yes, it's bounded above by, say, 2, 3/2, 1.6, and so forth. And the question is, does this have a least upper bound in Q? Well, we could say, well, what about 142/100? Would this be a least upper bound? Well, no, because we can find something even smaller. We can say that something smaller would be b is equal to 1415/1000, for example. Right? And we could keep going in this way. So the point here is that this set does not have a least upper bound in Q, but it does in the reals, right? We know that r squared less than or equal to 2 gives us r is less than or equal to 2 or greater than or equal to, root 2, negative root 2. And so r is going to be between negative root 2 and root 2. And so root 2 is the supremum of S. Okay, so the whole point of this was to show that this set in the rationals does not have a least upper bound, but if we extend the set to include the reals, it does, and that would be the square root of 2. All right, and so all of this is leading up to this theorem. So there exists a unique, complete ordered field, and we'll call this field the real numbers. So this is going to be the field where we're doing all of our analysis. Okay, so let's prove some properties about suprema and infima. The first one is that if the supremum or infimum exists, then it's unique. Okay, so let's do the proof for the supremum. So, let's suppose that alpha and beta are distinct sups of A. So remember, with these uniqueness proofs, we're gonna end up showing that alpha and beta are actually the same. So what does it mean to be a supremum? Well, since alpha is a supremum, it's an upper bound. And since we assume that B was a supremum, since B is a supremum of A, then all upper bounds of A are going to be less than or equal to B. In particular, alpha will. Okay, so alpha is an upper bound, beta is the supremum, so it's going to be less than or equal to alpha. And similarly, since alpha is the supremum and beta is an upper bound just by definition, alpha is going to be less than or equal to beta, and this implies that alpha equals beta by property 1.1 F. Okay, and this is a contradiction, right? Because we assumed that alpha and beta were distinct. So it must be that supremum of A is unique. And so as an exercise, you should prove that the infimum of A is also unique. Okay, so here's a big theorem, 3 stars, meaning you should really understand it and learn it and love it. If you have a subset of the real numbers, then the supremum of that set is equal to alpha if and only if, number 1, alpha is an upper bound of A, and number 2, given any positive epsilon bigger than 0, alpha minus epsilon is not an upper bound of A. That is, there exists some x in A for which x is greater than alpha minus epsilon. So let's try to dissect what this is saying here. Okay, so let's just look at this set 0 to 2. So we know that the supremum of 0, 2 is equal to 2. Okay? And we want to show that alpha minus epsilon is not an upper bound of A for any epsilon, no matter how tiny. So, show 2 minus epsilon is not an upper bound of A. Okay, so here's our supremum 2. And if we have, maybe epsilon is, I don't know, a half or something, and you're right here. Okay, 2 minus epsilon. That's not an upper bound of A. Why? Because you have things larger than that in the set. Okay, so it's not an upper bound. And actually, no matter how tiny you make epsilon, like if you make epsilon super tiny to where it's really, really close, right? You're still gonna find something bigger than that, right? In your set. You're always gonna have this property, and we're gonna make this rigorous later on by using what's called the Archimedean property. But that's the idea here, is that no matter how tiny epsilon is, you're always going to find something in the set that's even bigger than 2 minus epsilon. Like, always. Okay? So that's the intuition here. Let's see. And so part 2 is the analogous definition for the lower bound. So the infimum of a set A is equal to beta if and only if first beta has to be a lower bound of your set. And given any positive epsilon, beta plus epsilon is not a lower bound of A. So let's do the same kind of thing here. We know that our infimum is 0. And so why is it true that 0 plus epsilon is not a lower bound? Why is this true? Because we can always find something in that set smaller than 0 plus epsilon. No matter how small I make epsilon, I can always find something smaller and smaller and smaller here that's getting closer and closer to 0, but never actually touches 0. So for instance, I think I kind of mentioned this in the other example, but if you say, okay, well, let's play that game. If you say, well, how about epsilon equals 1 over 100? I don't know why I'm talking like this, but if epsilon is equal to 1 over 100, is 0 plus 1 over 100 a lower bound? No, because there's something even smaller. For instance, 1 over 101 is smaller than that. And then you could say, well, what about epsilon equals 1 over a billion? And I could say, and it's really close. I can't even draw it that close, but I can say, 1 over 1 billion and 1 is even smaller than that. Okay, we can continue this game forever and ever. And like I said, we're going to make this rigorous. Using the Archimedean property, but that's the intuitive idea here, is what these two statements are saying. So let's go ahead and prove part 1 of this theorem. So this is an if and only if statement. So we want to prove the forward direction and the backward direction. So for the forward direction, we want to show that supremum of a set A equals alpha implies 1 and 2. Okay, so proof of this forward direction. Suppose supremum of A is equal to alpha. Well, 1 is just true by definition, because if alpha is the supremum, it's already an upper bound, just by the definition of what a supremum is. Then 1 holds true by definition. Okay, so 1 is true. Now we just need to show that 2 is true as well. So we want to show that given any positive epsilon greater than 0, alpha minus epsilon is not an upper bound for A. So to show that 2 holds, let epsilon be greater than 0. And you should get used to that statement, let epsilon be greater than 0, because you're going to be hearing it a lot. So let epsilon be an arbitrary positive number. Okay, then we have, well, if epsilon is greater than 0, and if I multiply both sides by a -1, remember that reverses the inequality, so that means that negative epsilon is less than 0. And if I add alpha to both sides, I get alpha minus epsilon is less than alpha. And what does this tell me? Well, we assumed that alpha was the supremum. We assumed that alpha is the least upper bound. So there cannot be an upper bound smaller than alpha, right? Alpha is the least upper bound. So that means that alpha minus epsilon is not an upper bound. This shows 2. Or this is 2. Whatever. I can't write or think today. So given any epsilon, alpha minus epsilon is not an upper bound for A. So we just showed that. Okay, so we're done with the forward direction. Now for the backward direction, we want to assume 1 and 2 and prove that sup A equals alpha. So assume 1 and 2 are true. We want to show sup A equals alpha. Well, we're going back to the definition of what it means to be a supremum. It means that it has to be an upper bound, number 1, and number 2, it has to be the least upper bound. Since we assume that 1 is true, okay, that means all we have to do is show that alpha is in fact the least upper bound. Okay, so we already have for free that alpha is an upper bound. We need to show it's the least upper bound by using what we have with 2. Okay, so we're going to proceed by contradiction here. I mean, you can do it a few different ways, but I think that's the easiest. So since we assumed, I'm just going to write it all out just for clarity. 1 is true. Alpha is an upper bound for A. All that's left to show, right? We're trying to show the supremum is alpha. All that's left to show is that alpha is the least upper bound. That is, if M is another upper bound for A, then alpha is less than or equal to M. Okay, that's what we're trying to show. And we're trying to use number 2 to do it. So given any epsilon greater than 0, alpha minus epsilon is not an upper bound for A. So let's keep that in mind here. And let's assume, for the sake of contradiction, that m is an upper bound for A, but that alpha is not the supremum. So assume for the sake of contradiction that we have alpha is greater than m. Okay, so we're assuming that alpha is not the supremum. We took an arbitrary upper bound, and we're going to show that this results in a contradiction. Okay, so if I do some manipulation, if I just subtract m from both sides of the inequality, I get that alpha minus m is greater than 0. And up here, number 2, which I'm allowed to use since I'm proving the backward direction, for anything, any epsilon bigger than 0, any number bigger than 0, alpha minus epsilon is not an upper bound for A. Oh gosh, who's calling me? Let's see if I can silence this. Okay. All right. So where was I in my train of thought here? Right. This is bigger than 0, so I'm going to take epsilon to be alpha minus m. Well, again, by part 2, alpha minus m, right? I'm choosing that to be my epsilon, is not an upper bound. But y'all, alpha minus m is just m. This is a contradiction because alpha minus m is equal to m, and we assumed that m was an upper bound of A. Okay? So what we assumed had to have been wrong. So this means that alpha is not greater than m. So alpha is less than or equal to m, and hence alpha is the supremum of A. And we are done here because we've showed the forward direction, okay? We've showed that if you assume the supremum is alpha, this implies these two things. And then we showed the backwards direction. If we assume these two things, then that implies that the supremum of A is indeed alpha. Okay, so let's look at an example here. So suppose that A is the set of real numbers that are less than 0. So another way we can write the set is as follows: the interval from -infinity to 0, not including 0. And we want to prove that the supremum of A equals 0 with this theorem that we just learned, theorem 1.3. So we want to show two things. The first thing is we want to show that 0 is an upper bound of -infinity to 0. And I think this is clear because just by the definition of the set, we know that 0 is an upper bound of -infinity to 0. So in other words, 0 is going to be greater than or equal to x for all x in -infinity up to 0, but not including 0. So that's just definition stuff. And the second thing we need to show is that for all epsilon greater than 0, we want to show that 0 minus epsilon is not an upper bound. i.e., there exists x in our set with x being larger than 0 minus epsilon. Okay? So the idea here is we want to just pick a random epsilon, right? So the proof here is we want to just choose an arbitrary epsilon greater than 0. Well, same trick as before. If we multiply both sides by -1, it flips the inequality sign, so we get negative epsilon is less than 0. And so we just need to show that there exists some x in here with this property, right? Such that x is bigger than negative epsilon. And so if you think about it for a moment, we know that if epsilon exists, negative epsilon is less than 0. And so negative epsilon over 2 is bigger than epsilon, right? Because epsilon was assumed to be a positive number. So if we let x equal negative epsilon over 2, this negative epsilon over 2 is in negative infinity to 0, right? Because epsilon was assumed to be a positive number, so this is always going to be on the left side of 0 on the number line. And negative epsilon over 2 is greater than negative epsilon, right? Because epsilon was a positive number. So negative epsilon over 2 is going to be greater than negative epsilon. So again, here's 0, here's negative epsilon over 2, here's negative epsilon, and then all of the rest of the real numbers to the left of it. Okay, so that's it. X equals negative epsilon over 2 satisfies condition 2. It's in this interval. It's in negative infinity to 0, and negative epsilon over 2 is bigger than negative epsilon. So supremum has to be 0 because condition 1 and 2 imply that the supremum is 0. So the next theorem we're going to talk about has 3 gold stars, and that means it's really important. So it's called the Archimedean property, and it's very simply stated. So it's stated that if you have any real number x, there's an n in the natural numbers such that n is bigger than x. So give me a real number, I'll find you a natural number bigger than it. And it turns out that this is really, really useful and is going to be super important. So, make sure you have this in your pocket when you're doing these sort of proofs. So part 2 is just a specific instance of this. 1 over y, if y is a positive real number, then 1 over y is a real number. And by part 1, I can always find an n in the natural numbers that's strictly bigger than that guy. And then if you rearrange the inequality, you get 1 over n is less than y. So give me some positive y, I can find a number smaller than it that is positive. Which kind of makes sense, right? Because we were playing that game earlier. If y, let's say that this is 0, right? And maybe this is y. Maybe y is like, I don't know, a 10th or something like that. You can find a natural number such that 1 over n is less than a 10th, right? I can say, well, what about 1 over 11? That's less than a 10th. What about 1 over 12? And so forth. You can keep playing this game. So that's the idea. You can always find, if you're given a positive real number, you can always find a number smaller than it. A positive number smaller than it. So we're going to use these in some of our proofs. So let's get going with this one. Let's see. Okay. So, let me clear this. I think I was writing on it and forgot to erase it. Okay, so we want to show that the infimum of the set 1 over n is 0, where n is a natural number. So remember, we want to show two things. The first thing is that, so we're looking at lower bounds, infimums. So we want to first show that 0 is a lower bound. And that's clear because 0 is less than or equal to 1 over n for all n in the natural numbers. Okay, so no proof needed here. That's just the definition of the set gives that to us for free. Okay, and the second thing that we need to show is that there exists some x in 1 over n. Well, actually, maybe I'll just write it like this. There exists some 1 over n in our set for which for all epsilon, maybe I should write it like this, such that for all epsilon greater than 0, 1 over n is less than 0 plus epsilon. Okay, so we want to verify these two properties from theorem 1.3. All right, so the first one we've already done. So for the second one, for 2, let's do some scratch work. So this is a common thing in analysis. You're going to do some scratch work off to the side first to see what you're trying to get, and then you want to go back and like write the proof. So I'll show you what I mean. So we want 1 over n less than 0 plus epsilon, which is epsilon. And so we're trying to figure out what little n has to be for this to hold true, okay? So we'll just isolate n by multiplying both sides. And remember, n is a natural number, so multiplying it by both sides of the inequality isn't going to flip the inequality. No problem. It's always going to be positive. So this turns out to be n is greater than 1 over epsilon if you do the manipulation. And so this is the little n that we want. Okay, and we're going to play this game quite a bit in this class. So make sure that you understand this example because it's important that you understand this kind of like working backwards and then proving based on what you got with the scratch work. Okay, so this is what we're trying to show. Okay, we're trying to show that there exists some 1 over n in our set so that for all epsilon bigger than 0, this number in our set, 1 over n, is less than 0 plus epsilon. Okay, so what is that 1 over n? Well, let's see. So for our proof, we always start with the famous last words. Let epsilon be greater than 0. Okay? Get it tattooed on you. I don't care. We're gonna say it a lot in this class. Why epsilon? You know, that's a good question, and I don't know the answer. I know that we do have a history guy in our class. I'm not gonna say names, but if this person knows and they want to shoot me an email, I'm interested in why epsilon is used so much in analysis. I don't know. But anyway, okay, so let epsilon be greater than 0. By the Archimedean property, choose little n in n such that little n is bigger than 1 over epsilon. Okay, so we were given a positive epsilon, and the Archimedean property says you give me any positive real number, whether it be epsilon or 1 over epsilon, and I guarantee you I can find a natural number bigger than it. Okay? So choose that n. Therefore, we rearrange the inequality to get what we wanted back up here. Therefore, 1 over n is going to be less than epsilon. And so, of course, 1 over n is less than 0 plus epsilon. And we're done. Okay, so we found a 1 over n in our set such that for all epsilon bigger than 0, 1 over little n is less than 0 plus epsilon. And we did that by just using the Archimedean property. Okay, so let's see if we should write anything else. I guess we should just say, therefore, so since 1 and 2 are satisfied, 0 is the infimum of our set. So for this example, we want to show that the supremum of this set is going to equal 1, where the set is 1 over n, and n is a natural number. So we want to show the two things from theorem 1.3. The first thing is 1 an upper bound. That is it true that for all x in this set, 1 is greater than or equal to x? And yeah, that's true, because if we just start writing elements of this set, we see that as n gets larger, the sequence 1 over n is strictly decreasing. And so our set is going to be, when n is 1, we get 1 over 1. When n is 2, 1 over 2, and so forth. So the set is strictly decreasing, and so we do indeed have 1 is bigger than or equal to any x in this set. Okay, so that's true. And the second thing we want to show is for all epsilon greater than 0, there exists some n such that 1 over n, so something in our set, is going to be greater than 1 minus epsilon. In other words, 1 minus epsilon is not an upper bound. Okay, we can find something in our set that's actually bigger than 1 minus epsilon. And we don't really need to do any kind of hard work here, because when n equals 1, we get 1 over 1. 1 over 1, is that greater than 1 minus epsilon for any epsilon bigger than 0? Well, yeah, that's always true. We have 1 is always greater than 1 minus epsilon for any epsilon bigger than 0. And so this holds true because of this inequality. Alright, so the supremum of this set is 1, and as we mentioned earlier, the infimum of that set is 0. So let's look at this example. We have a set A is equal to n plus 1 over n plus 2, where n is a natural number. And we want to prove that the supremum of A is going to be 1. So again, by theorem 1.3, we want to show those two properties. And the first one is that 1 is actually an upper bound for A. So is 1 always going to be greater than or equal to n plus 1 over n plus 2 for all n and n? Is that true? Okay, so we can do some algebraic manipulation here with the inequality. Since I have n plus 2 on the bottom, natural number plus 2 is always positive, and it's never going to be 0. We don't have to worry about division by 0, and we don't have to worry about flipping the inequality sign when we multiply. So if I multiply both sides by n plus 2, I get this. And then if I subtract the n off, I get this always true inequality. 2 is greater than or equal to 1. So then if you do some backwards engineering, you see that this is always going to be true. So yeah, 1 is going to be an upper bound of this set. Now let's check the second property. So we want to show for all epsilon bigger than 0, there is some n such that n plus 1 over n plus 2 is greater than 1 minus epsilon. In other words, 1 minus epsilon is not an upper bound for the set. So we can find something in the set that's greater than 1 minus epsilon. Okay, and so with these sort of problems, you want to do some backwards engineering. So I'm going to write that as scratch. Remember, the whole thing with this stuff is we're trying to use the Archimedean property. So you want to isolate your little n so that you know what to choose for little n, like how big to choose it. So you're playing a game here. I give you an epsilon, you give me a little n that satisfies this inequality. Okay, so the scratch, let's go ahead and isolate little n. So we have n plus 1 over n plus 2 is greater than 1 minus epsilon. So if I add epsilon to both sides, n plus 1, n plus 2 plus epsilon is bigger than 1. Okay, and then if I go ahead and multiply both sides by n plus 2, it's going to give me n plus 1 plus epsilon times n plus 2 is greater than n plus 2. Okay, at this point I can cancel some n's here, just subtract them off. And then I can subtract off a 1 to give me epsilon times n plus 2 is greater than 1. Okay, so dividing by epsilon, I get n plus 2 is greater than 1 minus epsilon, and therefore n should be greater than 1 over epsilon minus 2. So this is the game, right? This is the little n that I need to choose in order for property 2 to work. Okay, so, you know, I give you an epsilon. Say I give you 1 over 100. Well, 1 over 100 minus 2 is 98. So my little n that I choose better be bigger than 98 for this to work. And I can always do this because of the Archimedean property. I can always choose a natural number bigger than 98. How about 99? Yeah, so anyway, this was the backwards work. So let's go ahead and actually do the proof. So this was the scratch work. All right, so the proof for showing part 2. We're going to let epsilon be greater than 0 be given, right? So the property says that for all epsilon bigger than 0, this needs to hold true. Choose little n in n such that little n is bigger than 1 over epsilon minus 2. We can do this by the Archimedean property. Now, sometimes I'm lazy, sometimes I'm not. I don't know if you guys can relate to this, but basically, you know, once you're at this point, you can just reverse engineer everything to get here, right? So that n plus 1 over n plus 2 is greater than 1 minus epsilon. So I'm going to leave this as an exercise. Then the result follows. So again, we want to, manipulate what you have to get n plus 1 over n plus 2 is bigger than 1 minus epsilon. Okay, and so that's the proof. So you should fill in the details. So in this example, we want to prove that the supremum of the open interval from 0 to 2 is equal to 2. So the first claim is that 2 is an upper bound of this set. And that checks out just by the definition of the set. So for all x in 0, 2, 2 is certainly going to be larger than or equal to x. And that's all it means for 2 to be an upper bound of the set. Okay? And for the second case, we want to show that 2 is the least upper bound. So to prove this, let's suppose that it's not. Okay, so suppose that 2 is not the supremum of 0, 2. Suppose instead that alpha in 0, 2 is the supremum. So the idea here is that we want to contradict that alpha is an upper bound for 0, 2. And so if I draw a little picture and just kind of, let me just write that this is scratch work in orange so that we can kind of neglect it later. So the idea here is, okay, here's our open interval from 0 to 2. And so we're claiming that there is some alpha in between 0 and 2 that's the supremum. That is, everything else in the set is less than or equal to it. But from the suggestive way that I drew my picture, this is not true, right? We can find something, say, right here that is strictly greater than alpha, and that would contradict that alpha is the is an upper bound for the set. So that's kind of the idea here. And so the idea is to, let me write this as idea, find an epsilon, positive epsilon, small enough so that alpha plus epsilon is still in the set. Okay, and that's going to give us this contradictory number. Okay, so that's the idea here. And so what we can think about here is if I take 2 minus alpha, here's another idea, 2 minus alpha over 2. Okay, so 2 minus alpha is going to be somewhere right here, right? 2 minus alpha. And if I have it, so this is 2 minus alpha. If I have it, it's just going to be this guy right here. So this is 2 minus alpha over 2. And so the idea here is to make this 2 minus alpha over 2 my epsilon and show that when I add 2 minus alpha over 2, I'm still getting something in my set, and it's larger than alpha. It's strictly larger than alpha. Okay, so that's the idea here. I just wanted to kind of give you the intuition of where I'm going to be getting these numbers from. Okay, so let's continue our proof in black now that the scratch work is out of the way. let's just box this up to ignore it for now. Continue. Continuing. So choose epsilon equals 2 minus alpha over 2. Okay, we know that this is strictly bigger than 0, right? So we can choose an epsilon in this fashion. And it's strictly bigger than 0 because alpha was between 0 and 2. So 2 minus alpha will certainly be positive since alpha is between 0 and 2, but not equal to 0 or 2. And then you have it and you're still positive. So no problems there. Okay? So then, remember what I'm trying to do here. I'm trying to, maybe I'll make it a little bit more clear here in the scratch work. This guy is going to be alpha plus 2 minus alpha over 2. So I'm trying to find this little epsilon so that I get a contradiction of alpha being an upper bound. And so that's this guy right, like if I add on epsilon to alpha, I get alpha plus 2 minus alpha over 2. So then alpha plus epsilon is going to be alpha plus 2 over 2. Right? So since I know that epsilon is 2 minus alpha over 2, I just added alpha to both sides to get this. Okay? All right. So now we're getting closer to our goal. Notice that alpha plus 2 over 2 is between 1 and 2. Why is this? Well, because we assumed alpha was between 0 and 2. If we add 2 to everybody, we get alpha plus 2 is between 2 and 4. And if we divide everybody by 2, we get alpha plus 2 over 2 is between 1 and 2. Okay? Therefore, so what can we conclude from this? Well, we know that alpha plus epsilon is greater than alpha because epsilon is something bigger than 0, so adding something to alpha is certainly going to be bigger than alpha. And moreover, since alpha plus epsilon was this guy, and we showed that this guy was between 1 and 2, alpha plus epsilon is in our interval. And this contradicts alpha being an upper bound. Right? Because we found something in the set that was larger than alpha. Okay, so alpha can't be an upper bound. Okay, therefore, our original assumption had to have been incorrect that 2 was not the supremum and that alpha was. So, because we have a contradiction, this means that 2 is the supremum of 0, 2. Okay, and we're done. And there's a few different ways you can go about this. I find that using a number line, especially when you're dealing with intervals that are nice and non-negative, I don't know. I find that drawing the picture really helps me understand how to go about this. But if you can prove it a different way, then that's totally fine too. Okay, the last thing that I really want to harp on in this lecture is another consequence of the Archimedean property, which is density. Okay, so in particular, the density of the rationals and the reals. So let's give a definition first. Okay, so if A and B are ordered fields like the reals, then A is dense in B if for any x and y in B, with x less than y, there's some A in between them. So yeah, so like here's your x and your y, and being dense in the set B, so x and y are from B, means that you can always find a little a that's in the other set between them. And so what we're going to show, so we'll show that Q is dense in R, meaning that between every two real numbers, no matter how close together they are, between every two real numbers, there is a rational number. So in our picture, we have our number line. Here's x real, and y could be really close, like that. Well, I'm not going to do that just for the sake of the picture, but here's y real, and we can always find a q, or maybe I'll just write it like this. We can always find a over b such that a and b are integers. We can always find a rational between two reals. So let's go ahead and prove this. I think your book has a little bit of a different proof than I want to give here, but you know, it's fine, I think. If you're curious, you should read the book for their proof. And I think it's like a bunch of different proofs of this, but let's go ahead and do it. So we want to prove that the rationals are dense in the reals. And so how are we going to do this? Well, we're going to assume that we have two positive real numbers. And as an exercise, you can try this proof. Try this proof when x or y is not in. So you could try, you could generalize it to where maybe your x is 0, your y is a negative real number, or they're both negative or something. But I'm only going to do the positive case for now, just for time's sake, I think. So I'm only going to consider the positive reals. Okay. So here's what we're going to do. We're going to assume we have two positive real numbers, and assume we always, by our order principle, we want one to be less than the other. We don't want them to be equal to each other. Okay? Now, we need to show that there exists some rational number m over n, where m, n are integers, specifically positive integers in this case, such that x is less than m over n, less than y. So m over n lives between x and y. So this is what we're trying to show. I'll put this in orange. And so here's the continuation of our proof. So we know by the Archimedean property that we can choose little n in n large enough so that 1 over n is less than the difference between y minus x. Okay? So this is just by the Archimedean property. We can always choose little n, like if you rearrange the inequality This says n is greater than 1 over y minus x. So this is a real number, and you can always choose a little n so that it's bigger than that real number. Okay, so just using the Archimedean property here. And if I just do some rearranging, just looking ahead to see what's happening here, I'm going to call this star. And rearranging the inequality, I get that x is less than y minus 1 over n. Okay, so that's our first step. And now we want to let m be the smallest integer greater than n times x. So n times x could be an integer, it doesn't have to be an integer, but we're going to let m be the smallest integer greater than nx. And I didn't list this as a corollary or anything, but this is kind of a corollary of the Archimedean property that we can always find an integer with this property. Okay, so because of this, we have the following. We have that m minus 1, which is an integer, right, because m is an integer, is going to be less than or equal to nx, depending on if nx is an integer or not, and strictly less than m. So m is the smallest integer greater than nx. So like if, for instance, this is just scratch work. So if nx is equal to the real number 5.9986, then your m would be 6. That's the smallest integer that's greater than nx, right? And then your m minus 1 would be 5. If nx is itself an integer, if nx is like 4, then the smallest integer strictly greater than 4 is 5. So m would be 5, and m minus 1 would be 4. And so that's where this less than or equal to is coming from here. Okay? So continuing on, just rearranging the inequality, this piece of it, I'm getting that x is less than m over n. Okay. So I'm just going to box this. Now using the other side of the inequality, since m minus 1 is less than or equal to n over x, this implies that m is less than or equal to nx plus 1, just rearranging here. And by star, this is going to be less than n times y minus 1 over n plus 1. Right? I'm just replacing x with y minus 1 over n, and x is going to be strictly less than that, so we know this whole thing is strictly less than n times y minus 1 over n plus 1. Okay. And if I simplify this, this becomes, let's see, ny minus 1 plus 1, so it's just going to be ny. And therefore, we have m so we have m less than ny, right? So m is less than ny. And rearranging for y, we get y is greater than m over n. And we're done, okay? Because we have our real number x is less than m over n, where m and n were both assumed to be integers, and y is bigger than m over n. And so we have that x is less than m over n, less than y. And remember, we're looking at things bigger than 0. So here's x, here's y, And here is our rational number that we just found, m over n. Okay, so that's the proof. All right, we will continue next week. I think we're going to do, I don't know what we're going to do. I'm debating on whether or not I want to skip the bijection chapter, but I don't know. It is pretty cool. So if you haven't seen that before, I do want to talk about it. I don't know. Anyway, thanks for watching, you guys, and I'll see you next time.